Dear learners, greetings from IIT Guwahati. Now we are in the another module of this MOOCs course, Applied Thermodynamics. The name of the module is Gas Turbine Engines. As the curriculum of this course, this is in the module B, IV, 4th. So, this particular module contains the following topics. In the first lecture, that is today, we will discuss about gas turbine engines, components, its thermal circuits. In fact, this particular lecture is mainly on introductory remarks of gas turbine engines. Then we will go to mathematical and thermodynamic analysis, that is gas turbine performance cycle for module 1 and also gas turbine performance cycle 2. That is the second lecture on this gas turbine performance cycle. And these two lectures will be devoted to mainly the thermodynamic analysis of air standard gas turbine cycles and subsequent enhancement of their performance. Moving further, in the lecture number 4, we will have a real gas turbine performance cycle, where we will introduce the concept of component efficiency and other irreversible factors that affects the gas turbine cycle. And the last two lectures, that is 5 and 6, will be devoted to aircraft propulsion cycle. Just to give you a background, that when we deal with the gas turbine engines, they are used in two motives. First motive is that we want to get the power, other motive is we want to get the thrust. So, depending on the requirement, the components are specified, and in aircraft propulsion cycle our main intention would be to get thrust, and in the other category, that is gas turbine cycle performance cycle, our main motive would be to get power output from a gas turbine engine. So, this is all about the broad spectrum of list of topics to be covered in the module 4, that is gas turbine engines. Now, let me start with the first lecture, that is gas turbine engines, and in this we will discuss about the components, different thermal circuit arrangements, and other subsection in this lecture would be the working feasibility, thermodynamic feasibility, and we will try to see that how a gas turbine engine is different from an internal combustion engine. Then we will move on to different thermal circuits. By thermal circuit I mean different components of a gas turbine engine are arranged in a particular fashion to have the complete cycle. So, this is known as the thermal circuits for gas turbine systems. And now we will give some introductory remarks to aircraft propulsion, how a gas turbine engines can be useful to generate thrust. Then we will have industrial gas turbines. So, industrial gas turbines are mainly intended for a rigorous power generation. If you want to use the gas turbine engines for a longer run, how the turbine or how the concept should look like. But however, our main intention would be a simple gas turbine systems that are used for power generation, number 1. Second thing, thrust generation. For power generation, we are mainly interested to find the work output. For thrust generation, we are mainly interested to get the thrust out from the exhaust of the turbine. So, let me start the background of these gas turbine systems. So, the concept of gas turbine systems came into existence after the Second World War, when people think that the aircraft propulsion systems can be modified so that we can generate the power. But originally their entire idea was to generate thrust in a gas turbine engine components. Many books refer these as aero derivatives. That means, initially the concept came from the gas turbine engines that are used for thrust generation in the aircraft, and those concepts are later on utilized to generate power in the ground based systems. So, those are called as gas turbine systems. But previously, before the gas turbine systems, there are many other methods that were in existence for power generations. For example, the mechanical power was produced by using working fluid, that is water, in hydropower plants, steam in steam power plants, fuel air mixture in reciprocating engines. Now, when you put this category, the reciprocating engines and gas turbine systems, thermodynamically they qualify as a steady flow processes, that is gas turbines, that all power generating systems they qualify as a steady flow processes involving different components, such as in a steam power plant we have boiler, we have pump, we have condenser, we have turbine, and all these things, entire components constitute a cycle, thermodynamic cycle. But however, each component has its own efficiency, and each component are organized in a fashion that it takes input from one and its output goes to other components. So, logically they are arranged in a particular fashion to have net effect to produce power output. And in fact, even same concept happens in the gas turbine power plant here, but instead of we will talk about what are the different components of gas turbine systems, but very bottom philosophy is that they come under category they call as steady flow processes. They are basically steady flow processes, and the analysis of these processes can be done through component analysis or as well as the global analysis. So, in the component analysis, for example, in steam power plant, the component analysis could be only concentrated for boiler, or it could be concentrated for turbine, or it could be concentrated for condenser or pump. But similarly, in a gas turbine system, we can have also similar manner in whether you have we are dealing with the compressor or a heat exchanger or a turbine system. So, that way we call this as a steady flow processes, and all these components runs steadily and continuously. So, they are categorized thermodynamically as steady flow process. But in contrast, when you look at IC engines, what we discussed in the last module, there some fuel comes in and air comes in. So, fuel air mixtures gives necessary energy to the system, and the piston cylinder and the gas, and as long as the gas is within the cylinder, there is no output. So, in that process, in one particular cycle, the entire system we can view is as a piston cylinder system. There is no non-flow processes as long as the gas comes and goes out. Okay. So, but however, so these gas turbine system or power generation system, they are called as steady flow processes, and these are non-flow processes. The other important aspects of this power generation system is that whatever method you use, the whether you go for a steam power plant or IC engine, but the maximum efficiency that is realized is about 40%. So, this has been proven thermodynamically that we cannot go beyond 40% efficiency. So, a steam power plant for instance producing a power of 1000 megawatt power has efficiency of about 40%. Okay. So, this was the essentially background when the power was generated before the Second World War. So, but after the Second World War, the concept of aircraft propulsion used in a turbojet engine. This turbojet engine was initially used to generate thrust in the aircraft. People thought of using this thrust, instead of thrust we want to get the shaft power. That means, we have to couple it with a turbine system, so that instead of thrust, which was supposed to be in aircraft jet propulsion system, we used to get power output. So, here it is a jet or thrust, here it is a work output or power. So, that was the essential idea. In fact, that was a huge success, and after that it finds tremendous applications in, apart from aircraft propulsion, it also finds the marine applications, electrical power generations with power generation as well. But here also this was also use the similar concept what we use in the IC engines. So, IC engine we use air plus fuel. So, here the but in a normally when you go for jet propulsion system or aircraft propulsion system, the fuel was typically aviation fuels or means high grade kerosene, but here this gas turbine system, the fuel could be natural gas, it could be a conventional diesel like what you do in a marine propulsion. So, that variety or variation is possible in a gas turbine engine systems. Now, apart from that, if you look at a gas turbine system, typically what happens, it consists of two major components, that is compressor and turbine, and they are coupled together, and side by side we have a combustion chamber where fuel is input. So, basically if you cut this particular part combustion chamber from the compressor and turbine, then the gas turbine system would operate. So, what you do is that here compressed air is used and it is fed to turbine. When it expands in the turbine, we get power output, but however we also require the power output for the compressors. So, in an ideal scenario, the turbine would develop a power that will run the compressors. That is the very basic or limiting stage for to have a minimum successful operation of a gas turbine engine. But that does not solve our purpose. We require more power. To have more power, what you have to do, you have to use the extra power from the fuel. So, the total power that comes out from the turbine, the sum power getting utilized to run the compressor, and rest of the power we can take it as a shaft power, that is for our electric power. So, this is the basic philosophy of a gas turbine operations, and in fact thermodynamically this heat addition process through a fuel is a constant pressure combustion, and for expansion of the gases in the turbine, a pressure ratio is provided through the compression of the working fluid, and typically our working fluid is always air. If there is no loss in either component, the power developed by the turbine is exactly equal to the power absorbed by the compressors. So, when they couple together, their combination would be no more than turn itself. That means, simply just turbine will drive the compressors, but here there is no output. To get higher output, we require fuel. So, that is what we need now. The application requires higher power to be developed by the turbine. So, hence additional energy must be added to raise the temperature of the working fluid prior to the expansion. Now, to do that we require fuel. So, since the working fluid is air, so use the concept of IC engine, where to initiate the combustion we require a constant pressure mode combustion as used in a CI engine. Now, once you have this, then expansion of this hot working fluid that goes from the combustion chamber to the turbine, it expands and gives a reasonable power to the compressor. Side by side it gives extra power output, and thus the use of a constant pressure combustion with a rotary compressor driven by the rotary turbine mounted on a common shaft gives the ideal combination of steady mass flow rate over wide operating range. So, this is the complete statement that says that how a gas turbine engine operates. A constant pressure combustion with a rotary compressor driven by the rotary turbine mounted on a common shaft gives the ideal combination for a steady flow operations over wide range of gas turbine applications. Now, let us talk something about working feasibility. That means, what are the limiting situations that a gas turbine system can work. The first, there are two main concerns here, is that when we are giving the energy from the fuel, that means the compressed air from the compressor goes to the combustion chamber. So, fuel is added. So, that fuel air mixture goes into the turbine. So, here the turbine inlet temperature when the fuel air mixture enters and expands, this typically very high. In fact, at different location of the turbine we will have very high temperatures, and since it is a continuous operations, high temperature material requirement becomes a necessity, because the thermal endurance that material is going to sustain over a continuous operation, as well as the thermal fatigue becomes important concern. And typically this temperature could be as high as about 1500 degree Kelvin. So, and that is a continuous 24-hour operation, and continuous operation gives the thermal fatigue. So, that means the whatever material that they are going to use in the turbines, there they should be able to sustain that thermal endurance. And in fact, that is one limiting case that decides the working life of the turbine blades. This is one factor, that means this gives the upper, this fixes the upper limiting case of operation. That means if your material is available for 2000 degree Kelvin, then if the materials are available, then we can go for that similar turbine materials. And other limiting case is that how much compression we can achieve through a compressor. In a realistic sense, although it is very easy to say we can achieve a pressure ratio of 30, 40, 50, 100 or so, but handling those high pressure ratio becomes a critical factor. So, the limiting case would be that at the same time when you say the components turbine or compressor, as far as talking about pressure and temperature, all these components should run at its best possible efficiency. So, that is what we call as a component efficiency. And in a gas turbine system, the minimum the compressor should operate at 85 to 90% efficiently, and turbine should operate of course similar range. Then only it becomes a viable options for power generations. So, this is what we call as a working feasibility. So, main important factor that could be component efficiency, the turbine working temperatures, and the what we say maximum air fuel ratio. So, all these three things becomes a deciding factor for working feasibility of a gas turbine engines. Then we will move to thermodynamic feasibility. Why we look for the thermodynamic feasibility? That if you look at this thermal circuit, we have a compressor turbine and we have a combustion chamber where heat is added through fuel. Now, here the question comes here that we have seen from IC engines, the heat addition from the fuel can be done through two different modes. One is like in SI engine we say it is a constant volume combustion, in CI engine we call this as a constant pressure combustion. But what will happen, and ideally both means can be possible for gas turbine engines, but in reality only constant pressure mode has a physical advantage or many advantage. First thing, that when you go for the constant volume combustions, this combustion of the fuel has to take in a constant volume, that means heat has to be generated from a separate entity and that has to be transferred again back to the air. So, this becomes a intermittent options, because it will not give you a smooth operations, and it is very difficult to integrate the air that goes out of the compressor and again heat that is coming from a combustor which operates through constant volume. Is synchronization of both these things is not a very difficult task. So, it leads to difficulties in smooth operations. So, ideally speaking, the constant pressure cycle is a better options, because it gives the continuous process of combustions, it gives the advantage of high mass flow regulations and handling higher flow rate. So, because of this reason the constant pressure combustion is a reality for a gas turbine power generation systems. And so, a gas turbine engines can operate with pressure ratio up to 35, component efficiency is about 85 to 90% and turbine inlet temperatures could be about 1650 Kelvin. So, this gives some realistic number the or maybe design parameters, if only then the importance of power generation through gas turbine engines can be realized. Then let us move to some basic differences between a gas turbine engine and internal engine systems. So, this is just a repetition, just what I have told or explained so far. So, IC engines are reciprocating type, so they are piston cylinder device, while gas turbine engines are rotary involve rotary compressor and turbines. Combustion in IC engine occurs either at we can have constant volume based combustion, that is in SI engines, or constant pressure based combustion in CI engine. Whereas in gas turbine it is only realized that it is only constant pressure mode. All the processes of IC engine occur in a single component, while different components are linked together in a gas turbine unit. So, whatever things that happens in IC engine, that is enclosed, the air fuel charge continuously compressed and expanded within these piston cylinder things, but whereas different operations are performed in a gas turbine engine, because compressor does its own job, it has to compress, the combustion chamber it has to add heat through fuel, turbine the gas has to expand. So, each component has its own role and they are linked together to give a consolidated unit, that is called gas turbine unit. The performance enhancement of gas turbine unit also involves additional components. So, whatever I have shown here, that we have, it is a simple system, but additional components are involved in a gas turbine unit for performance enhancement. We will see them in the subsequent class. That what are they? They are known as intercoolers, which is used between the compressors, that is mainly used that when we are going for high compression may be 10, 20, then single compressor will not solve a purpose. So, we need a multiple compressor and 2 or 3 compressors, but when you use 2 or 3 compressors together in a synchronized manner, then there must be an intercooler, because without which you will not get a best performance efficiency. So, that is the reason that we need to have intercooler when you have multiple compressors are involved. Similarly, when we go on to go for high power, I mean we want to go for very high expansion in a very wide range of pressure, then we have to use reheat options. So, we need to have reheat combustion chambers between turbines and afterburners. So, they becomes a necessity. So, when you add this in the name of performance enhancement, they add to complexity, weight and cost, and all these things will be only realized when they make a viable option in a commercial mode of power generation. Some other way of looking at other differences are the way the components are linked together in IC engines. Normally, they deal with the maximum efficiency, power output, rotational speed and torque. In fact, in a gas turbine unit, they have a versatile prime mover perform variety of functions, that is electric power generation, mechanical drive systems, jet propulsion supply system to process the heat and the compressed air. The components of a gas turbine units are linked together to produce either shaft power for electric power generation, that is what I was emphasized, electric power generation, or we call it as a shaft power. Other way we look at this thrust, which is mainly used in aircraft propulsion system. And in fact, for entire in this particular module we have will give emphasis how these two things are achieved thermodynamically in a gas turbine systems. The inefficiencies in the compression and expansion process becomes higher for a standalone gas turbine unit. So, and many times what happens, we go for a heat exchanger in a gas turbine unit, because this heat exchanger gives us the fuel efficiency. And when we talk about fuel efficiency, it will be at par with the conventional IC engines. So, having said this very broad spectrum or generic differences between an IC engine and gas turbine, let us move to different thermal circuits that are conventionally used, that we should know. Although we are some of the circuits we are going to analyze in our lectures, or some other circuits you should be aware of. So, first thing is that open cycle and closed cycle. So, the circuits, thermal circuits for open cycle and closed cycles are different. So, ideally, as the name implies, that open cycle means in one end the working fluid comes into the systems, and in other end the exhaust gas goes out of the systems. So, here in a open cycle system, air is drawn simply from atmosphere, and it is compressed in a compressor. Then it is fed to a combustion chamber, that means compressed air, where fuel is added, and so both fuel and air mixture comes out from the combustion chamber, and that they enter into the turbine, and finally after expansion exhaust gas goes out and we get the power output from the turbine. So, that means again the cycle goes, for the next cycle happens, fresh air comes again from the compressors. So, every time the fresh air always enters into the circuit. So, we call this as a open cycle, and in fact this open cycle are more visible or more useful as far as a gas turbine system is used, because air is available in plenty. So, normally we go for the open cycle mode as long as we have air available in the nature. And similarly, this is similar thing that we use in a steam power plant, where the fresh water is taken into the system. But where in some situations we require closed cycle, normally this closed cycle are preferred if the working fluids are become scarcity and then need to be circulated continuously in the circuit. So, in that case they operate in a closed cycle mode, where the compressor and turbine and there is a heater which takes heat output from the fuel from a separate unit, and there is also a pre-cooler, because the exhaust from the turbine should give out the heat to the some other fluid. So, this means same working fluid continuously flows in the circuit. So, this we call it as a closed circuit operation. The other mode that we call this as a combined steam and gas cycle. Ideally speaking, that the gas turbine systems, when it becomes a reality in a large power production unit, it becomes a reality or it becomes a feasible options if at all they are integrated with a steam power system. And such things we call this as a cogeneration mode of power generation, that means combined heat and power from through steam and gas, because it is very difficult to have to generate a megawatt power range only using a gas turbine system, because you need a huge compressor and huge turbines, and that too we need to have we have to play with very wide range of higher range of pressure ratio. So, instead of that, people think of combining a steam system with a gas power unit. So, what they have is that they have a common generator unit that or common power producing unit. In one side we have that steam power unit operates, other side gas power unit is operated, and both steam and gas power units are combined together. How they are linked together? Because power production from the both steam turbines from steam turbines and gas turbines goes to the common entity, that is generator or electric generator. This is one thing. Second thing, the exhaust from the gas turbine has typically very high temperature. That energy is utilized to produce steam. So, we call in a steam generator. So, basically that means this energy is used to generate the steam. And the other way of operation, that means except that the gas turbine units and steam turbine units, they operate in a independent manner. And why it is very significant way? Because the exhaust from the gas turbine is typically at a temperature 500 to 600 degrees centigrade. So, if you do that, it has been found that the combined role of steam and gas turbine unit has an ideal way of improving the efficiency could be as high as 60%. But had this gas turbine unit and steam turbine units operate independently, their independent efficiency would have been 40%, whereas when we combine them, their thermal efficiency could be as high as 60%. And in fact, in addition to that, other infrastructure, other things gets reduced, and other requirement of like for steam power plant, the requirement of fuel in terms of coal gets reduced, and in fact it is pollution free if you take the heat from the gas turbine exhaust systems. So that so in such case, we instead of conventional boiler, we can use a waste heat boiler or heat recovery steam generator. So these kind of words that are used in a combined mode of power generation in a combined gas and steam cycle. The next arrangement could be open cycle single shaft arrangement. First thing, we have emphasized that out of open cycle and closed cycle, open cycle is a best option. So, we will have to go for the open cycle arrangement and single shaft. So, the single shaft means the entire idea is that we have a compressor, turbine and shaft power. There are 3 rotating units and they are put in a common shaft. So, it is a what we call as a single shaft. So, power generation shaft and the compression and turbine, they are to be integrated. So, there are 2 important aspects. The turbine and compressor should be integrated through a common shaft. At the same time, power also comes out from another shaft, and if they are common, if it is common to all of them, then we call as a single shaft. Now, why we require single shaft? Because in many situations we require to operate the system at a fixed speed, fixed or base load power generation or fixed load conditions. So, the single shaft becomes a suitable. Now, if we have a multiple shaft system, then what will have synchronization of all these things will be different. So, once we set their synchronization things for all this in a common shaft, then it becomes easy to run that turbine unit. So, when they are in the single shaft, the high inertia drag due to the compressor reduces the danger of overspeeding in the event of electric load loss. Now, apart from this, when you want to have a single shaft, there is a requirement of heat exchanger. So, we need heat exchanger is a must. We will talk about why it is a must when you deal with the thermal analysis later. So, circuit must be added to improve the thermal efficiency. And also another issue could be a location of this combustion chamber. Many a times what happens, when the fuel is added into the combustion chamber and the entire fuel mass, fuel and air mass expands in the turbine. So, there the difficulties are there, the issue would be that the turbine blades are always get exposed to the combustion products in these continuous operations. So, when the fuel air mixture goes into this, but the other way of looking at that, instead of expanding that gas in the turbine, we only tap their heat. So, what happens in that case, what the circuit could be, there will be a separate combustion chamber where fuel is added, and that goes, when that heat get tapped through an heat exchanger, that means when the compressed air from the compressor enters to the heat exchanger, heat from this heat exchanger gets tapped by the air, and that high pressure and high temperature air enters. That means only air expands in the turbine, whereas in another mode, air and fuel mixture expands in the turbine. So, this is the very basic differences. Here it is air plus fuel mixture, this is only fuel, it is fuel plus air that expands in the turbine. So, basic drawback in this when the fuel and air when they expands in the turbine, because they erode the turbine blades. There is high chances of erosion of turbine blades, and that is not true when only air expands in the turbine. Then there is also some situation we require twin shaft arrangement. Twin shaft arrangement, in that there are some situations where it is required to operate variable speed and variable load conditions. That means, that turbine unit, gas turbine unit should be operated in a variable load and variable speed conditions, because your requirement of is such case. So, that case what we can do is that we can divide it into two shaft. One shaft, that means compressor and turbine, they are joined together and they are synchronized. Other is power turbine, or normally we call this as a free turbine. When we call it as a free turbine. So, that means turbine, this power turbine is a free turbine, it can produce power freely. It has nothing to do with the integrated shaft requirement for the compressor and turbine assembly. So, in such cases we may have options like is the exhaust, that means the whatever power required to drive the compressor, the turbine gives that power to the compressor. Now, after expansion it again goes to another turbine where necessary power is produced, and this power turbine is actually coupled to the shaft. So, this and both the shafts are different. So, that because in that way we can play with the variable speed and variable load conditions. So, there are certain advantages, like they can the turbine and gas and runs at the same speed, whereas power turbine can be designed to run at generator speed. So, because this power turbine can run at generator speed, and this can as a separate speed with among them, that is compressor and turbine can run in synchronization mode. A twin shaft turbine has a significant advantage, that is easy of starting compared to the single shaft unit. On the other hand, shedding of electrical loads can lead to rapid overspeeding of the turbines. So, if at all there is a rapid change in these things, only power turbine would be affected. Okay. Another thermal circuit arrangement could be open cycle mode, reheat and intercooling arrangement. So, thermodynamically we have seen that you must have also gone through and you deal with the steam power plant. But we use the concept of reheat, regeneration, etc. So, the concept of similar concept are used here, that reheat and intercooling concept. So, reheating, that means thermodynamically it is proven that in a single stage of expansion, suppose you are going for a expansion from wide pressure range. So, instead of going in a single mode, if you go for multiple stages, then your efficiency will go up. So, this and also power output will be higher. So, stage efficiency or stage power is more efficient than a single expansion. So, that is the concept that is used here, that we use multiple turbines and multiple compressors. The concept of reheat is used. So, instead of single combustion chamber, we will have a multiple combustion chamber, and in one case we call it as a primary combustion chamber, other case we call it as a reheat combustion chamber. What does it do is that after the fuel air mixture expands in the first turbine, they are allowed to expand in the next turbine, but before they are allowing, further heat is added. That means, instead of adding heat at a single unit, this heat addition takes place at multiple places, and the fuel air mixture is expanded in multiple turbines. And this concept we call it as a reheat concept. Other way of looking at in the compressor side, instead of going from a very high pressure ratio compressions, we use multiple compressors. So, the requirement of multiple compressor always leads to a fact that intercooler is a must. That means, after what does this intercooler do? First from the first stage compressor, the pressure goes up, also in the compressor also temperature also goes up, but this what we require is that we have to bring this temperature back to the atmospheric or back to the ambient conditions. So, this intercooler does not do anything on the pressure, rather it brings down the temperature to the back to the normal conditions. So, again this high pressure gas, but low temperature gas goes into the second compressors. So, we call this as a high pressure compressors. So, in this way the compressors are integrated through intercooling arrangement, and it has been proven thermodynamically intercooling and reheating always, because intercooling gives less requires less compression power, reheating gives higher net work power or work output. So, in both the cases your efficiency will go high. But one thing important thing to be noted is that the justification of intercooling and reheating is possible when we are looking for expansion or compression over a wide range of pressures. Pressure ratio could be more than 35-40, above that range the justification of reheating and intercooling is felt. So, this is what I have explained here. The performance of a gas turbine can be improved substantially by reducing the work of compression or increasing the work of expansion. So, at a given compression pressure, the required per unit quantity of working fluid is directly proportional to the inlet temperature. So, if the compression is achieved through two or more stages with intermediate intercooling, then it is possible to reduce the work of compression. Similarly, in the turbine output can be increased by dividing the expansion into two or more stages. So, reheating the gas to a maximum possible temperatures. The complex cycle can have a possibility of varying power output by controlling the fuel supply at the reheat chamber, so that gas generator can operate at optimum conditions. Okay, but however, the components, reheater and intercooling components gives the complexity to the system. Okay. There is another concept called as a multi-spool arrangement. Now, in some situation what we require is that we do not want other ancillary components like intercooler, reheater or something like that, but still we require high compression ratio. So, in that situation we call this as a multi-spool arrangement. That means, same high pressure and high compressor, same high pressure compressor and turbine are there, but that is a single combustion chamber. But what we do is that another, instead of going for a complex thermal circuit, if you want to go for a simple thermal circuit, then you decouple the low pressure compressor and low pressure turbine and try to synchronize, and they are linked in one shaft, and high pressure turbine and high pressure compressor are synchronized at their speed, so that, and they call it as a multi-spool. That means, high pressure turbine drives high pressure compressor, low pressure turbine drives low pressure compressors. So, this concept was used what we call as a multi-spool arrangement. So, in order to obtain high thermal efficiency without a heat exchanger and with a high pressure is required, then compression process puts a limitation. So, generally the compressor in the gas turbines are rotary in nature, because they have large fuel handling capacity, and in those cases at full power the density of outlet is very much higher than the inlet. On the other hand, the densities of compressor is too low at rotational speeds below the design value. So, this puts a limitation, unstable situations, because the of different handling different mass densities, and this becomes instability due to aerodynamic vibrations, because all these are the rotary in nature, and in some cases it leads to overheating of turbines. So, such cases we go for a multi-spool arrangement where the low pressure and low pressure turbine or compressor are integrated separately, and high pressure compressor and high pressure turbines are integrated separately. Okay. And the role of spool is felt when that means when you have twin spool engine gas turbine engines, its role is felt when the pressure ratio is above 35. Otherwise, you do not go for the multi-spool arrangements. Okay. Now, next part is that just to give some introduction about aircraft propulsion. As I mentioned, here when you only deal with aircraft propulsion, there we simply do not think about power developed from the turbine. What this turbine does? It does two things. One is it drives the compressor, that means it gives reasonable or sufficient power to run the compressor. Other is the exhaust gas is fed to a nozzle, and that nozzle gives the thrust. So, this is the very here there is no concept of shaft, there is only one shaft, turbine drives the compressor, but the exhaust gas that expands or there is a nozzle is used that gives the thrust, and this is the main concept of a simple turbojet engines. So, the greatest impact of gas turbine engine has been seen in the aircraft propulsion, because it has come in the since it has come into existence from the 19th century, and where the concept of turbojet engine or aircraft comes into picture, and there the entire idea is that to generate the thrust using a propelling nozzle, where this propelling nozzle or this nozzle was not a part of gas turbine units when you generate power, but becomes the nozzle is one of the important component when you in an aircraft propulsion systems. So, for low speed aircrafts, that is less than 200 meter per second, the combination of propeller and exhaust jet provides best propulsive efficiency. So, that is what we call as a turboprop engine. Also, we have another engine what we call as a turbo shaft engine that are mainly used in the helicopters. They use free turbine turboprops with power unit driving the helicopter rotor unit. Okay, so, there is a turbo shaft engine, turbo prop engines, and of course, there is a turbojet engines, and there is another latest variant what we call as a turbo fan engines. So, these are the different variants of aircraft propulsion unit in a gas turbine systems, but the very basic bottom line is that they all of them are used for thrust generations. Okay. So, this is what I have explained here. So, at high altitude, that means we require that about something about 200 meter per second, we require that means they all commercial aircrafts whatever they fly, this is close to Mach number of maybe 0.8. So, in that situation we use a engine what we call as a turbo fan engine, and that is the most efficient engine so far. So, in those what does there do is that a part of air is delivered by a low pressure compressor or a fan that bypasses to the rest of the core engine. That means, some component goes to this mode, other one goes as a bypass. So, we call this a turbo fan engine. Okay. So, these are the some of the summary, but another most important thing that heat exchanger has no place in aircraft propulsion system, because it makes the system as a bulky. So, only we have a simple combustion chamber. And another important aspect is that in airline application, the fuel consumption is a paramount importance that requires high bypass ratio, pressure ratio and turbine inlet temperatures. So, these are some critical feature, and we will touch upon some of the important aspects when you deal with the actual thermodynamic analysis. And the last segment I just give you some introduction about industrial gas turbine. So, when you are thinking this gas turbine to run in a industrial mode, that means it has to run continuously 24/7 365 days, you require a very rigorous lifespan. So, the lifespan is felt when we have 1 lakh hours without major overhaul. That is the requirement that a gas turbine engines in industrial mode has an efficient way of operations. But there is no limitations in the size and weight. So, the aircraft power plant makes an efficient use of kinetic energy of the gas leaving the turbine, which is not essential requirement for the industrial gas turbine unit. For industrial gas turbine units, they require, first thing is that they should not have major overhaul. Second thing, they should have continuous operation throughout year. Third thing is that we should think in their power production capacity in the megawatt range. But however, the concept of gas turbine come into existence only when it was realized that aircraft propulsion systems concepts can be utilized for power generation mode. So, that is the reason we call this, they are called as aeroderivative engines. The industrial gas turbines or gas turbine units, when they use for power production, they are aeroderivative engines. But when you say aeroderivative engines, when you say aero engines, fuels are different. They use kerosene, aviation fuels and any other high grade quality of fuel. But when they operate in a gas turbine mode for power generation, we can think of using natural gas, diesel or any other biogas or any other alternative fuels. So, finally, with a last remark that I say that aeroderivative gas turbines are widely used for application of gas, oil power, transmission, pipelines, peak load and emergency heat generation, and mainly this gas turbine for power generation is used in the marine or naval applications. So, with this I conclude this lecture for today. So, in the subsequent lectures we will discuss about the thermodynamic analysis of gas turbine systems. Thank you for your attention.